Here's a little notes video for you, trying to clarify and make very, very clear exactly what is acceleration. So I think we all have a sense of what this is just in like our regular everyday lives outside of physics class. But when we talk about things in physics class, we need to be very, very precise about our definitions and make sure we know exactly how to quantify, or in other words, put numbers on this. You know that if you're sitting at a red light, let's say you're sitting at the red light in front of Walmart, light turns green, you push down, or whoever's driving the car pushes down on the accelerator, the gas pedal, in other words, and the car starts to move forward. Now, what is going on there? Well, your speed is going from 0 when you're stopped to larger numbers. So it's changing. And what is acceleration? It's a change in velocity. If you got your cruise control on, you're on the interstate, you don't have any acceleration, right? So your velocity is not changing. But if your velocity is changing, either increasing or decreasing, then you have acceleration. Some people will call, when you're slowing down, they'll say that it's deceleration. That's just negative acceleration. That works just fine. You can call it deceleration if you want, but that's just a type of this. So change in velocity is equal to acceleration. Now, how do we actually measure this? So acceleration, which we're going to use a lowercase a for, is equal to change in velocity. But you wouldn't want to say, like, if you got on the interstate and you're like, oh yeah, I sped up and, I went from like 70 miles an hour to 75 miles an hour. Like, okay, great, but like, how long did that take you? In my Dodge Caravan, to get from 70 to 75, well, it's going to take like a little while, but in some other more sporty car, it might take less time. And that sporty car, I want to say that somehow it's like accelerating more, right? It might change from 70 to 75, just like my Dodge Caravan did, but it might do it in less time. So the time factor is important here. And just like velocity, was change in position over change in time. Right? So velocity is how much your position is changing relative to time, and acceleration is how much your velocity is changing relative to time. If the rate of change of velocity is constant, in other words, if like every second that goes by you add 1 mile per hour, 1 more second, 1 mile per hour. If the rate of change is constant, if it's the same intervals of time go by, the same increases in velocity happen. If the rate of change is constant, then we have constant acceleration. And that's what we're going to be interested in our unit here, constant acceleration. So what does a velocity versus time graph look like? It might look like, I'm not going to start it at the origin. It could start at the origin, like at that situation where you're sitting at the light, waiting for it to change, it turns green, and then your velocity goes up. As time goes by, your velocity is increasing. If you're like, wait a minute, that's exactly the same as the graph from the last unit. No, it's not, because this is velocity versus time. This is your velocity changing with time. In the last unit, this was position. And more about that in a second. So if you have constant acceleration, your velocity time graph will be a straight line because the rate is constant. That means rate and slope are interchangeable concepts. V versus t will be a straight line. And what are some of the things that we know about this straight line? Well, the slope of this, the rate of change is the constant acceleration, right? Change in v, that's rise, over change in t, that's run on this graph, right? So the slope is the acceleration. And this, you could call that vi, that's the initial or starting velocity. And the equation of this line, you think y equals mx plus b, but let's get the right things in here. So instead of y, this is velocity on this axis. V equals, and then let's see, instead of m, the slope is the acceleration. Y equals mx. Instead of x, you put the t there, plus b, but the y-intercept is the starting velocity, vi. And that's the equation for this line. And just one more thing I want to tell you. There'll be some more notes coming about this. One more thing I would like to remind you about, or maybe two, that, or maybe three. Remember that the area under a v versus t graph is the displacement. We saw that in the last unit. Now in the last unit, when you have constant velocity, then we might have a graph v versus t. With constant velocity, well, if the velocity is constant, then that's constant, right? And if you wanted to know, like, how much did, what's the displacement of this object with this constant velocity, you just have to find the area of that little rectangle there, and that's your delta x. With constant acceleration, our v versus t graphs are not going to be horizontal lines because the velocity is changing. We have acceleration. They're going to be these sloped lines. And if you want to know what's the displacement, you can do the same trick here with the area. Right? And you know, you took geometry. It's not hard area to find. Probably the easiest thing to do here, if you actually needed to do this, would be to cut that off and then turn it into like a rectangle plus a triangle. So nothing hard. And also remember that average velocity. Now our velocity is changing here, right? So we can talk about this average velocity is equal to displacement over time. If you have constant velocity, then there's no difference between your average velocity and your constant velocity because it's always the same. But now we have changing velocity, so you want to know your average velocity, find the displacement, divide by the time. And I think that that will do it, except maybe I just want to tell you that I want you to think about, if this is the v versus t graph, then what about position versus time? What does that look like? Ooh, there's some scary looking calculus there. Oh, look at that. So what does position versus time look like? So let's say we get that Walmart situation. I think you have some sense of this from your lab that you did at the beginning of this unit. So here's you with that red light in front of Walmart, right? And the light turns green and your velocity starts going up. what happens to your position? Well, your position goes up too, but this is not a straight line. If this was a straight line, then this would be a horizontal line. Then we're back to like unit 2, right? That's just constant velocity. So this can't just be a straight line. So how does the shape of this change when we have acceleration? If it was just a straight line, that would be constant velocity, and this would be like this, and we would have no acceleration to talk about. That's just cruise control on. So here, when we have acceleration, that is going to cause this to bend like this, in this case like this, where just like here when we have constant velocity, if this is a straight line, then velocity versus time is the slope of this. And the slope of this line right here is not changing. What's the slope? It's the same, the same, the same. The slope of the line is just a number, and the slope of it right here, and the slope of it right here, and the slope of it right here is just the same number. Now look at here, we have, if this is what those slopes are, they're getting steeper. So here, what's the slope of this here? Well, I guess it's like pretty shallow, right? It's like about 0. And then now here, well, it's getting steeper, right? And now it's getting steeper. So this going up means the slopes, that has to be bending up like that. Okay, so that should be good. What's that, about 12 minutes of notes for you. You should watch this before you try assignment number 2. Thanks much.